You guys, it's Mrs. Duskevich, and I just want to go through a few stoichiometry problems with you. One way to use this video would be great is if you would try the problem first, and then what you would do is just hit pause and hit play again after you've tried the problem, and then you can see how I've worked it out. So let's get started. First off, you'll see on each slide I have the stoichiometry steps. And so just going through the stoichiometry steps, one thing that students tend to have a question on is they get confused with the have and the need. And so what you do is you read your question, and to determine the have, you look at the information that is given to you. That's the information you have, and what is the information that you need. That's how you distinguish between the two. So if I were to look at this first slide here, what I would do is I'd go ahead and I'd have my ladder going on here. And my question is, how many grams of acetylene are produced by 5.00 grams of calcium carbide? So the first thing I think about is what I have. And what I have here is 5.00 grams of calcium carbide, and that's the information that's giving to me. What I'm looking for is grams of acetylene. And if you don't know what acetylene is, you go up to your equation and you find everything else you know how to name, but acetylene looks like this C2H2 because that looks like something you may not be familiar with. So when we come down here to our ladder, we always start with our have. And so our have here is 5.00 grams of calcium carbide. And that should say 5.00. That's my fault right there. But that's calcium carbide, so please make sure it says 5.00. And we need to find the molar mass of calcium carbide. So what we do is we take the molar mass and we find it to be 64 grams of calcium carbide. The way I found that was 1 calcium weighs 40 grams from their periodic table, and carbon weighs 12 each, but there's 2, so 40 plus 24. And that's per 1 mole of calcium carbide. So once we have our mole of calcium carbide and we're in the moles, we're ready for stoichiometry step 4, which is to create our mole ratio. Our mole ratio is used from the equation, so we come up here and we look at the coefficients from the equation because that's where the proportionality comes from. So according to our equation for calcium carbide, there's nothing in front of it, so the assumption is there's 1 mole of calcium carbide. Well, we want to do acetylene, so we look at acetylene, and when there's 1 mole of calcium carbide, there's simply 1 mole of acetylene. So I go ahead and figure that out, and so my mole ratio is just a 1-to-1 this time, which is totally fine and totally normal. Now at this point, I can cancel everything out because I can cancel my grams, I can cancel my moles of calcium carbide, and right now, if I were to solve, my answer would be in moles of acetylene, but I need grams of acetylene. So now I have to do my conversion. So I simply find the molar mass of acetylene, and again, I have 2 carbons at 12 each and 2 hydrogens at 1 each. So for every 1 mole of acetylene, I have 26 grams of acetylene. And when I calculate that, I'm going to get 203 grams of acetylene, but unfortunately, you guys, it should be 5.00 from the get-go. So if I kind of have my decimal in the wrong place, so just make note of that. The answer should be 2.03 grams. So I apologize for that minor mistake there. So the answer instead, you would have 2.03 grams. Okay, let's go on to the next one. How many molecules? This is a little bit different. Molecules, I'm going to have to use Avogadro's number eventually, of oxygen are produced by the decomposition of 6.54 grams of potassium chlorate. So again, don't get confused by all the extra words in there, but instead identify what you have, which is 6.54 grams of potassium chlorate, and identify what we're looking for, which is molecules of oxygen. So I come down here to my equation, and here's my potassium chlorate, and here's my oxygen right here. So to start, I have my ladder, and I'm going to put in what I have, which is 6.54 grams of potassium chlorate. First, I'm in grams, so I have to convert to moles, or I can't do my mole ratio. So I go ahead and I convert to moles, and my molar mass of potassium chlorate is 122.5 grams, and that's per every 1 mole of potassium chlorate. Once I get to potassium chlorate and I'm in moles, I'm ready for step 4, and that's my mole ratio. So I come up here to my equation and I have 2 moles of potassium chlorate when I have 3 moles of oxygen. Well, I want to put the 2 moles of potassium chlorate on the bottom so that I can cancel my moles of potassium chlorate, and I have 3 moles of oxygen on the top. So I have a 3-to-2 ratio. Once I have my moles of oxygen, I realize that I can't stop there because my answer needs to be in molecules of oxygen. So to go from moles to molecules, I use Avogadro's number, 6.02 times 10 to the 23rd. So I need to put 1 mole on the bottom so I can cancel, and that allows me to put 6.02 times 10 to the 23rd molecules on the top. Now when I go to put this in my calculator, I want to be extra careful because once I multiply across the top, I want to equals, divide, and then I'm going to put parentheses around 122.5 times 2 into parentheses. And if I don't do that, then my order of operations for my calculator will be all goofy. So then I calculate, and my answer is going to be 4.8 times 10 to the 22nd molecules of oxygen. Let's try another one. The equation for combustion of carbon monoxide is 2 moles of carbon monoxide plus 1 mole of carbon yields 2 moles of carbon dioxide. So my question is, how many liters of oxygen are required to burn the 3.86 liters of carbon monoxide? So I'm using liters here, so I'm going to have to use my molar volume of a mass, or molar volume, which is 22.4 liters. So the first thing I do is I line up my ladder, and I think, well, what is given to me? And that's 3.86 liters of carbon monoxide. And I realize I'm not yet into moles, so I need to convert to moles first. And so I'm going to use 22.4 liters for every 1 mole of carbon monoxide. Once I get into moles, I'm ready for step 4, which is my mole ratio. So I go up to my equation, and I have 2 moles of carbon monoxide when I have, and I'm looking for oxygen, 1 mole of oxygen. So I put my 2 moles of carbon monoxide on the bottom so I can cancel, and 1 mole of oxygen gas on the top. If I solved right now, my answer would be in moles of oxygen gas. But my question is, how many liters of oxygen? So I need to continue after my mole ratio, and I do have to convert to the need. I can't just stop at the moles. So I have 1 mole of oxygen is the same as 22.4 liters of oxygen. Now again, to calculate this, I would multiply everything across the top. 3.86 times 1, which you can if you want to, but if you don't have to, times 22.4. And I'm going to hit equals, and then I divide by, again, parentheses, 22.4 liters, or 22.4 times 2 times 1 end parenthesis. Again, for order of operations, and you should get 1.93 liters of oxygen. Finally, let's check out number 4, and we have rust is produced when iron reacts with oxygen. So I want to know how many grams of iron 3 oxide are produced when 12 grams of iron rusts. So again, the first thing I want to set up is I have the have and the need. So my have is 12.0 grams of iron, and I'm looking for grams of iron 3 oxide. So I start with my have again, which is 12.0 grams of iron, and I need to convert to moles because I have to have it in moles in order to do a mole ratio. So I look at my periodic table, and for iron, my molar mass is 55.8 grams of iron, and that's per 1 mole of iron. Once I'm in moles for iron, I'm now ready for my mole ratio. And according to my equation, I have 4 moles of iron, and I'm looking for moles of iron 3 oxide, and I have 2 moles of iron 3 oxide. So when I have 4 moles of iron, I have 2 moles of iron 3 oxide. There's my ratio. It's a 2-to-4 ratio. Notice I put moles of iron on the bottom so I can cancel from moles of iron. Now, if I want to, I have to look at grams, and I need grams of iron 3 oxide. But right now, if I'd solve my equation, I would end up in moles of iron 3 oxide. So I have to convert to grams one more time. So when I have 1 mole of iron 3 oxide, I have to find the molar mass of iron 3 oxide, which happens to be 159.6 grams of iron 3 oxide. Again, I'm going to multiply across 12 times 2 times 159.6 equals, divided by the quantity of, and again we want to put parentheses around, 55.8 times 4 into parentheses. And you should get 17.2 grams of iron 3 oxide. Hopefully you've taken some time to just practice, and then you're able to follow along with me to see if you're in the right direction. So use this to your advantage. Take care, you guys, and ask me for more questions. Bye-bye.